Dear learners, welcome to NIOS Studio. Myself, Dr. Triranjita Srivastav. Today, I will be discussing Module 7, Structure of Atom. In Part 4, we will discuss hydrogen spectrum. In this lecture, you will be able to understand the atomic spectra and we will determine the frequency and as well as the wavelength of the emitted radiation and in short hydrogen spectrum. Now, the question arises that what is a spectrum? A spectrum is a variation of energy with respect to frequency or wavelength. As you all know, electromagnetic spectrum, which varies from radio waves to gamma rays, that is having a wavelength of 10 to the power 3 meters to 10 to the power minus 12 meters, and corresponding frequency is also given over here. So, what is atomic spectra? Now, as you can see here, the word atomic means that we will prefer to use a gas or a vapor at a very low pressure. Now, in order to excite the atomic gas or the vapor, electric current is passed through it. Now, the excited atoms, due to the spontaneous emission, they will radiate certain energy. It was observed that in the emitted radiation, only specific wavelengths were obtained. This spectrum consists of bright lines on dark background, and this type of spectra is known as emission spectra. This figure represents the line spectra of hydrogen atom in visible region. In this, we can see 4 distinct lines in the dark background. The red line corresponds to 656 nanometer wavelength, whereas blue and violet, this corresponds to order of 400 nanometer. So, in this we see bright lines in the dark background, and hence it is a representation of emission spectra. In contrast to this, there is a absorption spectra, that is, when white light is passed through a gas, it was observed that some of the lines in the spectra were dark, that is, we get dark lines in the bright spectrum, and this was known as absorption spectrum. One of the distinct feature of this is that the dark lines corresponds precisely to those wavelengths at which the emission spectrum was observed. Like in this figure, we see the upper one is showing the emission spectra of hydrogen and the lower figure is showing the absorption spectrum. In the emission spectrum, we have bright lines on dark background, whereas in absorption spectrum, we have dark lines on bright background. And the lines are in one-to-one correspondence, that is, in both the spectra, the lines are appearing at the same wavelength. So, this is basically the property of the material which we are studying. So, what is the importance of studying the spectra? So, it basically serves as a signature of a particular element or the gas which is present. One of the important application is in astronomical spectroscopy for detecting the presence of various elements and calculating the redshift of stars. In order to understand the atomic spectra, let us recall what we have already studied, that is the energy of electron in an atom. It is given by the expression, that is En equal to minus mz square e to the power 4 over 8 epsilon naught square n square h square. From here we can see that energy in the nth state is inversely proportional to n square. This expression can be written as Ry z square over n square. Here Ry is the Rydberg constant of energy, which has a value m e to the power 4 by 8 epsilon naught h square. Now, if we substitute the constants, that is the value of m, the value of E, epsilon naught and h, the value comes out to be equal to 13.6 electron volt. Now this is a Rydberg constant of energy. In terms of this, the energy gets simplified in a very simple equation, that is En equal to minus Ry z square by n square. If we talk about the hydrogen atom, then Z is equal to 1, and this can be written in a much simpler way, that is En equal to, this will be plus E1 by n square, where E1 is the energy of the electron in the ground state. If we write the energy of the electron in an nth state for the hydrogen atom, it is given by En equal to E1 by n square, where E1 is the energy of the electron in the ground state, which is equal to minus 13.6 electron volt, that is for n equal to 1 state. This figure represents the energy levels in hydrogen atom. In this figure, we can see that for the ground state, that is n equal to 1, the energy is minus 13.6 electron volt. For the first excited state, n is equal to 2 and the corresponding energy is minus 3.4 electron volt. For the second excited state, n equals to 3 and the energy is minus 1.51 electron volt. So, as we go to the upper states, that is the other higher order excited states, the energy decreases with respect to n square. Here the minus sign represents that the electron is bound to the nucleus. For n equal to infinite, we can see that here it is written ionization, that is the corresponding energy is 0 and the electron is no more bound to the nucleus. As we have studied the Bohr's postulate, so according to the fourth postulate, the energy of the emitted photon having frequency nu when electron falls from initial energy state n to a final energy state m is given by h nu equal to En minus Em, where En represents the initial state and Em represents the final state. Now, if an electron is in the initial state, it will emit a radiation which has a energy h nu, which is equal to the difference between the two energy levels, and by emitting this radiation, the electron comes to the final state, that is in the ground state. From here we can derive the expression for the frequency of the emitted radiation. So, this can be written as E1 1 by n square minus 1 by m square. Again further this can be written as 1 by m square minus 1 by n square. Here m is the final state and n is the initial state. Again if we write this expression, so this will come out to be equal to E1 by h 1 by m square minus 1 by n square. As we know that E1 is equal to minus 13.6 for hydrogen atom, so here itself it is having a minus sign. So, when we substitute over here, we will get the frequency which is positive. So, the frequency of the emitted radiation is given by this expression. Here we can introduce a subscript, that is nu mn. This means that this is the frequency corresponding to the transition from the nth state to the mth state. The electron which is in the excited state, nth state, this will make a transition by the emission of a radiation having a frequency nu mn. The corresponding wavelength of the emitted radiation is written as lambda mn, which is represented as wave number of the emitted radiation. So 1 over lambda Mn is the wave number, which is equal to minus E1 by Hc 1 by m square minus n square. This can further be simplified as 1 over h. Corresponding to this frequency, we can define the wavelength, that is 1 over lambda Mn will be equal to minus E1 by Hc times 1 over m square minus 1 over n square. These equations can be further simplified by substituting minus E1 by Hc equal to R, which is a universal constant known as Rydberg constant. After substituting the values here, we get R equal to 1.09 into 10 to the power 7 meter inverse. So, these expressions get simplified as the corresponding frequency is given by nu Mn equal to Rc 1 by m square minus 1 by n square. So, these are the simplified as well as master equations by using which we can very easily determine the frequency as well as the wavelength of the transition lines in the hydrogen atom. Now, we will show the energy spectrum diagram of the transitions in the hydrogen atom. As we have already seen, the energy for ground state, that is n equal to 1, is minus 13.6, for n equal to 2 minus 3.4, n equal to 3 minus 1.5 and so on. Now, there will be transitions from excited state to different states. That is, the first transition will occur from n equal to 2 to n equal to 1, then n equal to 3 to n equal to 1, n equal to 4 to n equal to 1 and so on. Further, we can have transitions from n equal to 3 to n equal to 2, n equal to 4 to n equal to 2, which means that all the transitions for which the final state is same has a particular series. Here it is given as Lyman series, Balmer series, Paschen series, bracket series. So, these are the different series which are obtained in hydrogen atom. This we will study in detail in the next lecture. So, what we have learnt is in this lecture is atomic spectra. We determined the frequency as well as wavelength of the emitted radiation and studied a little bit of hydrogen spectrum. Thank you.